Okay, hey everyone, I'm Luca. I'm head of research at Altubit, and I've been working for 1 year now on native rollups. Like right here at Berlin Blockchain Week, I got taken by some folks at Ethereum Foundation, and they asked me whether that there was this interesting new direction of native rollups, and given the work that I do, on L2s, if I could help with this, right? So 1 year later, native rollups are mostly a solved problem, like at least in theory. There were a lot of open questions 1 year ago. And now I'm working on making them even more powerful. And this more powerful version of native rollups is this native proof verification primitive. So this talk is based on this ETH research post that I published. And there is a QR code here. I also have the same QR code at the end, so don't worry. The research, all my research, is based on EIP 8025, which is optional execution proofs. What this EIP tries to do is to basically define all the primitives in Ethereum to be able to verify blocks using ZK. So in the future, in the near future maybe, if you're running a validator, if you're running an attester, you will be able to attest without having to execute the blocks and without having to hold the state, just by verifying a ZK proof. And again, what this EIP does is just defining all the primitives, like the spec to do this, but this will be an option. And this is more or less what it looks like, right? So what will happen with this EIP is that there is a proposer. A proposer usually delegates block building rights to a builder. A builder then builds a block, but also needs to generate a proof. This builder will delegate to a prover. And then you have two kind of attesters. One that is a full attester that gets the block header and the block body and executes the block body to check whether the block header is correct. Or the other one that takes the block header and a proof without the block body. It doesn't execute anything, it doesn't have the state, but it can still say whether the state transition is correct and everything else is correct because there is a ZK proof. So what is the difference between optional proofs and mandatory proofs? So for this EIP, this research, I need mandatory proofs. And the only difference between optional and mandatory proofs is that like when we have optional proofs, we need to still, as I said, provide the option for full attesters to actually execute the blocks. There is this EIP that limits the hardware requirements for an attester. And if we still want to allow full attesters in the network, we cannot increase the limit, the gas limit too much. The only way to increase the gas limit over a certain point is to require proofs. Because the only way to stay within these requirements is only if you verify a ZK proof. And this is for like very high gas limits and very high throughputs, right? So first we're gonna do optional proofs. We're not gonna increase the gas limit, and then when we're confident that this thing works, we're gonna increase the gas limit and require proofs to be able to stay within these requirements. So like looking a little bit more closely on how this L1 proof infrastructure works, in practice what will happen is that a prover will not just generate one proof, but it will need to generate multiple proofs. And this is because of proof diversity. In the same way that we want client diversity to be able to detect bugs, we need proof diversity. And this proof diversity is done in two ways. The first one is we want diversity of the ZK VMs. These are the RISC-V machines virtual machines that will be ZK proven. And there will be multiple of them. For example, one can be Zisk, as Jordi presented. It can be OpenVM, it can be Pico. There are multiple ones. And then, on top of these RISC-V machines, you run an Ethereum client. And we also want diversity of these Ethereum clients. So this can be Geth, this can be Nethermind, this can be Ethrex, Aragon, whatever. And you could do potentially, like, as long as this program can be compiled to RISC-V, you could prove any of these programs, right? And then testers, to attest to a block, they will require some consensus, some quorum of these proofs to agree on the result. So like a few months ago, I think the Ethereum Foundation was trying to have a 3 out of 5, so an attester will attest to a block only if there are at least 3 proofs that agree. I talked yesterday to Justin Drake, and he told me that they're moving to a 2 out of 3, actually. So an attester will need to have 2 proofs. It's a 2 out of 3 because a prover can stall, can have a liveness failure, and you don't want that to block the network, right? The important thing is that all the machines, the virtual machines that we're planning to use are RISC-V machines. And I want to give you an intuition on like what it looks like to run a program on top of a RISC-V machine in practice, like on a ZK-proven RISC-V machine. So as an example, I'm going to use SP1. Again, SP1 is a RISC-V machine. This is a verifier that is used on chain. That is the address, and you can see also the projects that use this address, like SP1 verifier. There are multiple ones of them. There is Mantle, Celo, Avail, and so on. All these programs that are being verified on RISC-V are different programs, but they use the same RISC-V machine because it's a virtual machine. It can run different programs, right? But it's the same one. And the way that it works in the smart contract is this. You have a verify proof function that takes the program, and this program is a bytes 32. It's a hash of a program. Then it takes the inputs to this program, and then it takes a proof, right? And then when you actually want to call the verify function, what you do is that you take the program hash, you take the public inputs, you put them together within one input, and then you verify a proof and the input. Like the most important thing to understand here is that the program being verified is just an input to the verifier. So now the idea is, if Ethereum for itself has this RISC-V verification infrastructure that it uses for the EVM, why not exposing the same RISC-V verification infrastructure for all programs on Ethereum to use? They're not just EVM. They could be anything. Like all the programs that use ZK proofs, instead of having to deploy their own verifiers and maintain them and fix them when there are bugs, they could just reuse the infrastructure that Ethereum is already planning to enshrine. And this is the idea behind what I'm working on, which is proof carrying transaction. This would be a new transaction type that provides you with a program that you're verifying, the inputs to this program, and the proof. The proof is verified on the consensus layer within the same infrastructure that validators and nodes will already use for L1. This is more or less what the spec looks like. You have a verify proof function that takes a proof in the same way that I showed you in the smart contract has a proof public input. The public input is a program hash and the public values. The public values are basically the input to the program. But the program hash is arbitrary. And the thing is that for a verifier to verify an arbitrary program is the same cost as any other program. So it's not more difficult. So this is a new transaction type. It adds these 2 new values. And to give you an example again, let's say that someone deploys Typhoon Cache. This is a ZK application for privacy, an imaginary privacy application. This uses ZK proofs for privacy again, and for succinctness. And this uses this native proof verification infrastructure. So the user would create this proof carrying transaction. It will generate the proof. The proof goes to the consensus layer. It passes the program hash, and all the validators, they have this RISC-V infrastructure that will just verify the proof using the same thing. And then on the EVM, they're basically, if the transaction does not revert, it means that the proof has passed, so you can take the inputs and use them within the EVM. Like, you will not verify the proof within the EVM. There will be 2 new opcodes just to know that the program hash is correct and the public values are correct. But that's it. It's actually a little bit more complicated than these, just because these proofs are very large in practice. And these proofs will be Starks, will be quantum-resistant ZK proofs. And these proofs are 300 kilobytes. So if there are a lot of people using these transactions, a block becomes very big very quickly. So the idea is these proofs will be shared within the mempool, or will be propagated within the mempool, but they will not end up in the final block. Once they reach the proposer will just take the proofs and generate a recursive proof. So at the end of the day, when you get a block, you just get one single recursive proof that also proves the verification of the single proof-carrying transaction proofs. So including the Typhoon cache program in this case. And I'm mentioning Typhoon cache, but this is, again, this can be used by all applications that use ZK. This can be used by all the L2s with arbitrary programs, so not just the EVM. This can be used for privacy application. It can be used for anything, really. And again, the main benefit is if there is a bug here in the ZKVM stack, this is a bug that also exists on L1, and L1 will fork for you, will fix it for you. You don't need to worry about bugs in ZKVMs. So if you remember, some time ago, Vitalik was discussing this idea of moving from EVM to RISC-V. And my take here is that maybe we can do this through these proof-carrying transactions. This is not like RISC-V directly, but this is basically some sort of ZK RISC-V where, yes, you can write programs in Rust, in C++, in whatever you want. And you can verify them natively on L1, but only through ZK proofs. And if this thing works well, maybe we can also do it on L1 directly as programs that are native on L1. But this is like almost the same thing, in my opinion, because at the end of the day, you need to generate a ZK proof. And that's it. This is what I'm working on, and thank you.